Stromfee Report Office Building, Cologne.
And this is what it looks like over there on Bayer Stress. We have our Stromfee diary with them. This Stromfee measuring device, the Ammonio, we're now going to connect it to the main connection first, so we can see the flow directions when power is being fed in from the battery, when it's being fed in from the PV system, when the heat pump is drawing power, when the air conditioning unit is drawing power, and when the tenants are drawing power. No, the sub-distribution, not the tenants. There are no tenants here. And then we'll have a transparent picture from the energy center. That's what I meant. It's already quite interesting to see. So, in a building, no biogas plant, no large-scale PV system, but in a moderate building, 3 or 4 measuring devices installed in the right places to turn flying blind into flying by sight, even though they already have smart meters here. They all have smart meters, but they're not smart. They're just digital dumb meters. They've been around for 20 years already. There's nothing smart about them. That's not what I wanted to show. The only idea was to take a really close look for once. Yeah, it says 17313, and that's what the lady here has as well. That was the commissioning together with Romy. And here we've installed a digit the eye of the electricity ferry, meaning an optical scanning head, on one of the meters for testing purposes. And now let's take a look at what came out of it. So here we can see exactly the PV system depending on the weather. We can also see this flow through the installed measuring point. How much is being consumed? How much is being produced, that is, taken out, and how much is being fed into the grid? Of course, through the battery, obviously. That's pretty clear, I think. The battery, quite intelligently, if you take a really close look, let's zoom in here. Here come the data. It takes a little while. After all, it's not just one customer in there. First, the house is supplied with electricity, then the zero feed-in rule kicks in. The battery only tries to draw power when necessary. Of course, there are switching operations with the PV system. It doesn't balance out that quickly either. That's the thing. It's what makes it so complicated. Only when there is a surplus does the battery charge until it's full, from 9:30 to 12:30. Then it's full. The rest of the PV system's output is then fed into the grid. The sun sets, there's still some consumption, and the battery discharges, basically keeping the power drawn from the grid at 0 until 11:30 at night. That means from 9:30 in the morning to 11:30 at night, for over 12 hours, the house doesn't draw any power at all. In fact, even more is fed into the grid. So, if we were to double the battery capacity, we could extend the period of no power draw from the grid during the night by quite a bit. And that's what the Stromfee diary is for, to help you size the battery properly. Specifically, you can use the active energy output of the PV system. You have to take average values, say, from March to October or November, and then compare those values with each other. And that's how you can size the battery. In this case, we haven't created any balances yet. Instead, during the first half of the year, we're closely observing these ratios to discuss with the customers how large the battery might eventually need to be. Let's go back to the 7-day view. We can also briefly take a look at the 30-day view, and then it becomes clear that you really have to be a pro if you want to interpret these dashboards. Not everyone has the time or desire for that. So here, too, is the nice 7-day view. You can really study and observe all of this in detail. But that's exactly why we developed our Stromfee AI system, and that's what we're going to look at now. We're here on the server stromfee.graphics. I've entered the dashboard here. It's been running since the 1st of June. For testing purposes, of course. And it runs twice a day. Now we can take a look at what the results interpreted with the standard prompt look like. We have the dashboard here, and every 12 hours a report is generated, so let's take a quick look. It reads out the prices and gives us a report. It has recorded the outside temperatures and looks at the total output. No anomalies. Once again, a value for the PV system, just like we saw in the last video. The battery performance is being assessed. A plain text summary is generated in this form. The graphics on discharge and charging behavior are studied and evaluated. It also notes that there could be a storage bottleneck. So this is the standard prompt without going into any special features of the system. And all of this happens every 12 hours. And if you don't feel like reading it, you can have it output as a video again, and that's what we're going to take a look at now.
The data shows that the maximum price is at 150 euros per megawatt hour and the minimum price is at 2.26 euros, indicating significant price fluctuations. The current amount of 10.3 euros shows that the price has been moderate in the past few hours. Outdoor temperature trends. The outdoor temperatures fluctuate between a maximum of 29.0 degrees Celsius. And currently, it's 17.2 degrees Celsius. These temperatures show a clear pattern of cooler nights and warmer days, which is typical in the summer months. An average value of 21.1 degrees Celsius could indicate an overall mild climate. Total power consumption of the house. The maximum power consumption of the house was 7.04 kilowatts, while the current consumption is at 5.80 kilowatts. However, the minimum value of 214 watts shows an interesting deviation. This could indicate a temporary drop or a negative feed-in. Photovoltaic system, PV system. The PV system generates a maximum output of 26.8 kilowatts, with a current value of 3.92 kilowatts. Here, there is a clear discrepancy between the maximum and current value, which is probably due to changing weather conditions. Battery power. The batteries show a maximum output of 18.3 kilowatts. However, a negative value of minus 385 watts is shown for the average output. This seems to represent a challenging situation as the batteries might be in a discharge state. A current value of 54.0 watts shows that, despite the negative balance, a certain amount of power is still being provided. Power flow of the PV system. The complex graphical representation of the PV system's power flow shows some significant fluctuations. At certain points, sudden increases in power are visible. This could indicate brief sunny periods. Overall, however, the trend appears to be decreasing, which may indicate the need for performance optimization. Battery operation, charging and discharging. The graphs of the charging and discharging behavior of the battery storage show that during certain periods, high charging power comes from the PV system. However, it is also striking that the discharging at certain hours exceeds expectations, which could indicate a potential storage bottleneck. Summary. The analysis of the presented data reveals significant insights into the system's energy efficiency and dynamics. The price fluctuations on the electricity exchange as well as the varying temperatures play a significant role in the energy strategy. An optimized use of the PV system and battery may be necessary to improve the overall energy balance and minimize the deviations between maximum and minimum outputs.